right, we are officially at 2 o'clock. For those who don't know, this is a hybrid event. So that's why we have kind of our tech Twyla here with the camera and speaker up here for people to hear our speakers and hopefully interact within the activity later today. For those viewing virtually, if you can't hear us, if you can't see us, we have Katie on our tech side as well for the virtual people. So if you have an issue, please put in the chat and we will be happy to fix those things as they come. But welcome to today's hybrid event, Energy Modeling Translating to Real World Decisions. This is a second in our high performance design series for 2024, providing a format to engage with presenters and attendees alike. My name is Miranda Wright. I'm the Education Engagement Manager here at Illinois Green Alliance. And before we get into today's presentation and working session, I'm going to do a quick run through of who we are at Illinois Green. I need to turn this on. There you go. For those who are unfamiliar, Illinois Green Alliance is a membership-driven nonprofit organization that advances green buildings and sustainability communities for all. Our 5-year strategy plan pushes the green building industry to meet or get on the path to net zero. We achieve this work through educational events such as today, as well as panels and building tours, by engaging communities and partnering with organizations across Illinois, and by advocating for new policies and legislation. Learn more about membership, upcoming events like this, and get involved by visiting our website. See if this works now. Hey, this webinar is approved through AIA for 2 continuing education credit and can be logged for 2 lead AP or Green Associates continuing ed hours as well. Certificates of completion for both AIA members and non-AIA members are available upon request. And that's what this QR is for. This is for AIA credits and for architectural license certificates needed for those. If you are here to get the CE hours for your lead AP or lead Green Associates, that will come in some self-reporting instructions in a follow-up email after today's event. So this is just for licensed architects. Here are our AIA learning objectives for today. And then also would like to take a moment to recognize Illinois Green Alliance's sustaining sponsors who make all of our work possible. A special thank you to our gold level sponsors, ComEd, USGBC, and Sloan. You can make a commitment to advancing green buildings in communities across the state by visiting our sponsorship page on our website and starting a conversation with me. So I thought before I pass it over to our presenters for today, I would just give everyone a snapshot of what we're going to be doing in the next 2.5 hours. So we're going to start with some presentations, both some slides as well as in the program of the RETScreen and Sketchbox, and then hopefully some time for Q&A, a bathroom break, and then an activity between 3:30 and 4:20 that we'll be working with our presenters as well to work through those. And then hopefully end it with kind of an activity discussion, talk about what people ran into, issues they had, things they learned, etc. And with that, I would like to introduce our speakers. I will let each of them kind of introduce yourselves, where y'all from, your background, etc. But we have Ajit. Ajit, I didn't ask how to say your last name before we started.
Naik.
Naik. From Baumann. So excited to have you here with the Vice President and Director of Building Performance Analytics. And then we have Ben Heymer from Slipstream, the Director of Engineering. And with that, I'm going to pass it over to Ajit.
Thank you. This guy working, or do we use the buttons?
It is working, yes.
Oh, nice, cool. Well, thank you, everybody. Appreciate the intro, Miranda. Yeah, I'm Ajit Naik with Baumann Consulting. We have an office right upstairs. It was really convenient getting here. So we share an office with Illinois Green Alliance. They're great roommates. So glad to be here. So I'm here to talk to you guys a little bit today about energy modeling and specifically translating it to real world outcomes. We as a firm, and me personally, I'm very driven by coming up with ideas, testing ideas, but also then seeing them through to reality. That part is really, really important to me. And energy modeling is one of, a set of tools that we have to make that happen, to help kind of give people the confidence and the information they need to make decisions. So through my presentation, I have a few kind of goals for you here. I want to learn about, really what's motivating people to establish real, measurable energy and GHG performance goals. I want to talk about predictive energy modeling and how it differs from compliance energy modeling, the distinction some of you might be aware of, and kind of how to use it, in design processes for new buildings, for existing buildings. And I'm very passionate about existing buildings for reasons which we will get to shortly. And I want to kind of go through an existing building case study and kind of walk you guys through a software that we use for that RETScreen. So just a question. I don't actually have polls here, so you don't have to answer. But what are folks' backgrounds here? We have engineers here? All right, great. Give a show of hands. Architects? Great. Facility owners or developer owner side? Manufacturers? Who am I missing? Folks who didn't raise their hand. What are your backgrounds?
We work for an organization that supports electric vehicle infrastructure.
Cool. All right. Awesome. So support organization.
Insulation.
Insulation. Awesome. Love it. Love it. Great. Good. So it sounds like we have a pretty diverse group here today. So try to keep that in mind. So I wanted to start out by just talking about some motivations here. So I'm sure a lot of you have already seen this stuff, so I won't spend a lot of time on it. But carbon emissions today, for those who are concerned about environmental impact, which I guess is most people attending an Illinois Green Alliance event, buildings and their operations and the time and effort we spend on building them, account for almost 40% of our carbon emissions today, right? Like that's a fact this year, last year, this number bounces around between 30 and 40%, but it's basically been at that for a very long time. So, we have had done a lot of things about this, since the 70s, when we had a first oil crisis, energy prices were really high. People were waiting lines outside of gas stations. So to do something about it, we implemented building energy codes. For the first time in 75, we began to say, hey, you need to think about energy efficiency before you're even going to be allowed to build a building. And, it kind of bifurcated, split into a commercial version and residential version. But all these codes over time have been marching on and getting more and more efficient, to the point where most modern codes today are like result in a building that's only half as energy intensive as it was back in 75. So we've come a long way. That's actually made a big improvement. We can actually see that. So this is another great graph from the Energy Information Administration publishes trends like this. And actually, so building energy-related carbon emissions. So this isn't normalized or anything. It's like actual emissions. We actually peaked, right around 2005. Energy codes, if you look back at the graph, right around 2004, they took a big jump in performance, and you can actually see that, right? Like, our track carbon emissions, lots of things happened over time. We switched from coal to natural gas, but it's undoubtable, that the switch to energy efficiency and energy efficiency codes have had a big improvement. And we've seen that energy building related carbon emissions have dropped, but that rate of dropping is slowing down. We're starting to kind of plateau out, right? And in fact, if you look at the current future projections, we're gonna really not make much of a difference at all. This is accounting for increasing efficiency in new building codes and energy efficiency. Maybe 10 years from now, when I give this presentation, we'll be 60 or 70% better than 1975. But even accounting for all of that stuff, the EIA is kind of imagining that we're gonna flatline in terms of carbon, right? It's kind of a perverse outcome, you think, despite all these changes. But even though energy is improving, carbon kind of isn't. And it's the same really on both residential and commercial, right? Like we are getting to a point where we need to do more. And the issue at hand really is existing buildings, right? Like if you own an existing building, be it a house or a commercial property or what have you, in most places in America, like you're good, right? Like you don't need to care about the building energy codes, right? Like you only care about those when you do a major renovation or a new construction. So, 40% of the, or 2/3, 66% of the building stock is existing, globally. So that means like almost 2/3 of our buildings, regardless of all our efforts for net zero new design, making all these energy codes for new construction, 2/3 of buildings are like never going to get dinged, really by any of this and are kind of existing outside of that whole framework. And you can see that reflected here, right? So no matter what we do with new construction and all the renovations and work that people are going to do, there's this big, opportunity, both a challenge and an opportunity of existing buildings, right? And how we can improve them so we can start driving that line down further. So there are actually many ways that municipalities, governments, regulatory bodies are trying to do this. Right? And one of the first things and easiest ways you can do to help existing building owners kind of start paying attention to this is to make them track it, right? And that is called a benchmark. So we have one right here in the city of Chicago. We have since 2012. Qualified buildings, I think it's over 50,000 square foot every year, have to report their utility bills. There's a platform that the government sets up, the US government, the EPA, to allow municipalities to collect this data. You got to report it every year, and you get fined if you don't report it. Right? So, I mean, how many of you know how much money is in your checking account right now? Yeah, probably everybody, I'm gonna guess, right? Or at least maybe not to the cent, but at least to within a couple bucks, right? And so there's a reason for that, right? Because you care about how much money is in your bank account. And one of the easiest ways to care, one of the easiest things to do, or the most beneficial things to do is check up on it so you know what's in there. So it makes sense with what you expect. So a benchmark ordinance is kind of the first step. It's like your online banking app. Let's see, check it. Well, a benchmark ordinance kind of forces you to look at your bills and report it to the government. And there's a little stick to fine you if you don't report it. This is enough to make a lot of people think like, wow, damn, I'm really not doing that well compared to pure buildings, or like, really, I'm a real poor performer. Those of you guys who have a comment account, which I guess is probably most of you, may be familiar with those little report cards that they send you comparing you to your neighbor, trying to shame you, right? It's the same, or reward you if you're more efficient than your neighbors. So that's one of the tools that we've had and we've seen, over the last 10 to 15 years. In Europe, they've been doing this for 20 plus years, but a little bit behind the curve on the energy efficiency here, but we see them. They're all over the place. Many municipalities have them. Oak Park recently passed a law implementing this. Evanston has had one on the books. They even make you track water up there, but this is one of the tools. Another way, if you don't care, lots of people will be like, so, I'm not paying my utility bills. I rent my space out to tenants or whoever, and I'm not paying the bills. Like, do I really need to care? So the next level is building performance labeling regulations, right? So this exists on top of it. Not only do they make you report your energy usage, but the government will then kind of give you a rating. Those of you who have been to New York may be familiar with the restaurant rating system that you see on the doors there. Every restaurant has an A through a D grade. If you go to that D grade joint and see the cockroach run out front, you might think twice about whether you eat at that establishment. And the idea here is by requiring performance labeling for these buildings that potential renters, tenants, other people, stakeholders doing business, have a means to kind of know whether this building meets their needs or not. So it's kind of more of a shame aspect to it, right? Like, not only do you have to report, but if you're not doing well, you really have to deal with the public shaming. And if you are doing really well, you can brag about it. So enforcement is a little bit lackluster. There's a lot of buildings. I haven't seen one for this building in the lobby, though it's qualified, but I did see one at Costco on Ashland the other day. So 3.5 stars are pretty good. But the way that this works is by comparing you against your peers, right? So you'll see that it uses the Energy Star score, which is a means of comparing your building against similar buildings nationwide and comparing it on a curve, right? If you get a Energy Star score of 100, you're best in class. You're more energy efficient than all the other peer buildings in the data set. If you get a 0, well, you're the worst. 50, you're right in the median, right? You're the average building. So that's usually how we talk about it, the Energy Star score. Just as a sense, you can compare your building against kind of the nationwide average. And the Chicago energy rating system works that way too. Lots of other municipalities have these laws, are rolling out laws like this too. What's next, right? Some people are truly unashamable. Maybe some of you know somebody like this in your life. I sure do. But the next step really is a bigger stick. So a building performance standard, which we don't have here in Chicago yet, doesn't give you a certificate of performance. It does that, but then it also gives you a fine if you rank below a certain level of performance, right? And these fines can be quite significant in some cases, which we'll come back to later. So if you, this isn't here yet, right, in Chicago, and I think I'm missing a slide here, but Chicago, along with several other municipalities, has signed on to President Joe Biden's Building Performance Standard Coalition, by which they agreed to implement a standard like this. So there are already all our laws like this in DC, in Washington State, in New York, exotically St. Louis, a few other places as well too.
Boston.
Denver, Boston, yeah, Boston. How could I forget? Yes. So these are real things, right? And it's a matter of time before it comes to Chicago. And the reason I really bring this up is this is one of the major motivators, right? Like a lot of people don't care about benchmarking. A lot of people don't care about performance labeling. But when you threaten somebody with hundreds of thousands of dollars of fines, everybody starts listening, right? And so not here yet, coming here soon, but wherever it exists, this is a major motivator for energy efficiency. Like nothing gets people listening like fines. So that begs the question, like, what do we do about this, right? We are architects, we're engineers, we're suppliers, we're advocates. Like, how do we do, what do we do about it? And one of the tools that we have is energy modeling, right? So like energy modeling, I pulled this, I thought it was off of Wikipedia, sorry, energymodels.com. Basically, it's this practice of making a virtual model of your building, like on a computer, and testing it to see what happens, right? People do this all the time, in automotive industry or in the aerospace industry, before you build a full-size mock-up and send it to the wind tunnel, right? You build like a virtual 3D model of your rocket or whatever, and you check it out before you spend all that money. So an energy model is really kind of the same idea, right? It's a virtual model of your building capable of, capturing everything in it, right? We got this projector here, we got that clock on the wall, the fire alarm system, the lights, the AV, all these people in here breathing, giving off heat and carbon dioxide. Building energy model is a simulation tool that can capture all of these things, predict how much energy that we're going to consume, and allow us to test strategies and kind of provide some feedback and identify, what are good things to do if you want to hit an energy performance target. So building performance simulation, just want to touch on this more broadly. It's really that it exists outside of energy too, right? It also exists for plenty of other building characteristics. People use this concept to check how light plays out inside a building, to optimize windows for daylighting. It can optimize natural and artificial lighting using different types of building simulation. You can even assess like the carbon content, like the embodied carbon content of different design strategies using building simulation. You can model airflow patterns throughout large spaces using different kinds of building simulations. So this is a really common technique in practice, that's used through all facets of building design and operation. But energy modeling is, really valid for anybody who really has a key performance goal. So as we kind of described, it involves building usually a 3D representation of the building. Not always. Doesn't have to have like a 3D physical model. You could just, punch in your wall areas, roof areas, just the general parameters. There's different ways and different tools, but fundamentally, you're defining key aspects that impact building energy performance, like weather, where your building is, its enclosure, it's the insulation on the walls, the roofs, the windows, how it's being used, occupants, appliances, things that are plugged in, lighting, HVAC, water usage, all of these things, you end up defining them to kind of match how you think the building is going to operate. And you get out lots of things. You get out energy use, right? Like how much energy is associated with this. You get peak loads. All this talk of electrification requires a pretty big electrical panel. The folks here definitely can talk to us about that. So having an understanding of, what this is going to mean for your infrastructure is also something that comes out of an energy model. So it's not just energy, it provides a lot of value. And of course, utility costs. Everybody cares about money too. Greenhouse gas emissions also are on there, other things that kind of build on energy. But fundamentally, that's the idea of energy modeling. And the way that we usually talk about our results of energy use is in energy usage intensity. Anybody familiar with this term? Cool. Anyone want to volunteer what the definition is? No volunteers? Who said yes? I saw somebody shaking their head over here. You?
Yes, it's total energy that's used by building in a year, I would say.
Yeah, and the key, yeah, per square foot, and that's the key part of it, right? It's normalized, right? It's the amount of energy per square foot, so that way I can compare two warehouses, even though one is double the size of the other. If I talk about their energy usage in terms of per square foot, it's a really useful means for comparing, right? Because if we're talking about using a model to make a prediction, you better have some kind of expectation of what you're going to get. You guys have heard garbage in, garbage out, right? So having this concept of what do typical buildings perform like, what do similar buildings perform like, so you can kind of set an expectation is a key aspect in energy modeling. And one of the ways of doing it is get familiar with these metrics like energy usage intensity. What do those look like for a typical school? What do those look like for a typical warehouse or a typical office, or whatever the kind of project it is that you might be working on. We usually break that down to several major end uses, things like fan energy, pump energy, cooling towers, lighting, chillers. So we kind of break it down a little bit so that you have an idea and a sense of where the energy is going in your building. So why do energy modeling? Obviously, you care about energy usage, but a lot of people don't care about it, right? And there's a reason to make them care. So we talked right at the beginning about energy codes, right? So one of the reasons you need energy modeling is if you want to get a permit, you need to comply with energy code. And one of the ways you can comply with energy code is to build an energy model of your building and show that it complies with code that way. So, in the city of Chicago, you might need it for the Department of Buildings for a permit. If you're going for a zoning change, you might even need an energy model to deal with the Department of Planning and Development, even before you get a permit, just to get a zoning change. They have a form specifically about code compliance and it has line items on the bottom specifically relating to energy modeling. So that's one environment in which you might run into this. Secondly is LEED, right? Who all here has worked on a LEED project before? Yeah, several hands, about half of you. So third-party certifications. So another major market driver for energy efficiency and sustainability has been things like LEED. People want to brag, right? If I'm going to do all the sustainability stuff, I want a way to kind of show that I'm doing this. The market values it. Stakeholders value it. Tenants might value it. Lots of big Fortune 500 companies have ESG goals. So when they look to rent spaces in offices, they make that one of their requirements that it be LEED certified in order to get it. So this has been a major market driver in the US and around the world. There are different versions, different certifications, but they all kind of share that aspect. And energy modeling is often required for these as well. There's a form in LEED, which some of you who've worked on this may be familiar with, maybe infamous. So but it's used to document the energy modeling process. So both of these things, whether it's for code or whether it's for LEED or a certification process, is a form of compliance modeling. I alluded to this earlier. So compliance modeling is a very specific application of energy modeling, right? What it does is it requires you to make energy model of your building. So you see two images there. It's like our building proposed design is the one on the top left. And then you're required to make an imaginary fictive version of your building that has all code minimum. That imaginary building is called the baseline, right? And you can see there's some things you take away, like if I have shading in my design, like the baseline won't have. So, it's typically worse. It's like a code minimum level of everything. Anything you do better than code, you're allowed to take advantage of it. And your design is compared to the baseline. And you typically have to beat the baseline. So for code, you just have to be better than it. For LEED, they give you points for being certain levels better than it. But fundamentally, the idea of this is compliance modeling. It's rating. Funny enough, it's not about predicting how much energy, right? It isn't at all. It's literally about comparing you against this imaginary version of your baseline. And you might think that's kind of strange and like why it works that way, but it's really similar to how we treat cars. Right, like I've never owned a vehicle ever in my 38 years of life that I've gotten the EPA rated mileage on, right? Because I got a lead foot. I live in a cold climate. I'm not always inflating my tires the way they should be. I'm not replicating the EPA rating conditions, and so I never get that. Same goes with compliance modeling, right? There's prescriptive values for how much you assume a school runs per year, right? Or like how much stuff appliances people have plugged into their apartments, right? But that varies. An apartment downtown with a bunch of young people versus like a senior home in Evanston, They're gonna have a totally different profile with how people use and plug things in. None of that is accounted for in compliance modeling. If it's of a type, they tell you how you use it. And it's the same way, same philosophy as rating a car, right? Because like you can't account for lead foot and grannies and everybody else. You have to have a standard set of rating conditions. Great for compliance, bad for predicting how much energy your building is going to use. So we're going to talk more about performance energy modeling, both Ben and I here today, because that's really what our passion is. And we're really trying to make a difference here. But this is the lion's share of modeling that you'll run into is compliance modeling. So the common codes you might run into, ASHRAE, IECC, these are different energy codes. They all contain rules for how to energy model. So predictive energy modeling standing away from compliance modeling is any energy modeling process when you actually want to predict like how much energy you're going to use. So it's not just about showing that you're better than an imaginary baseline, but damn it, I need to save utility bills, and I want this model to be able to help me to predict that. So it has all real world aspects. There's standard values in there, things that you don't know, like how are people going to use this like apartment, or how many appliances they're going to plug in. If you don't know those things, you run what if scenarios and see what happens. For those different things, you call it a sensitivity analysis. And then the idea is that you should be able to use this model to kind of close that uncertainty gap to test improvement scenarios and help advise on finding out, those measures which make sense, pay back, really reduce your energy. So just a kind of, again, high level summary, really compliance energy modeling, not about predicting. So if you're working on a project and there's an energy modeler, they're doing an energy model for code or for lead, that energy model is not likely to predict the actual energy usage. That's not what it's for, any more so than the EPA is trying to predict my personal likely rate of mileage, but rather rate the car in the standard set. So not going to talk anymore about compliance modeling here. It's a big deal, but that's not what we're after. We're after predictive modeling. So we can use this in two ways, and we're going to talk about this from two perspectives. First is from the owner perspective, right? Lots of times people who own buildings have really high energy usage or high utility bills, or they're subject to a performance labeling or a building performance standard, and they're like, oh my God, we've got to do something about this. And you build an energy model in that case based on what you see in the actual building. You talk to people, you look at documents, you go on site. One of the major benefits is you actually have utility bills, right? So when you build a model, you can match it to the utility bills. And if you're off, well, something in your model is wrong, right? And you can go through a calibration process. It also helps you to kind of cost things out. On developers or new projects, lots of us were architects here, working on new construction. New construction project doesn't exist. It doesn't have utility bills. What do you do about that? And that again, you handle with sensitivity analyses, right? You kind of say, what if I'm not sure how much equipment people are going to plug in. I'm not really sure what time, this school, if it's going to run over the summer or not. All these things that you don't know, you test them, right? Like what happens, right? And then you test your design decisions or your energy efficiency measures under all these different likely scenarios, and then pick the one that's most resilient to all the likely scenarios you're likely to encounter. So really those two aspects, right? For building owners, calibrate to their data, and for kind of new building designers and developers, you can identify those things that are uncertain and see what would happen, right? So it's useful for both predictive energy modeling. So really the process involves at the beginning, at the outset, establish goals. Like what are the performance goals? Like do you have energy goals, carbon emission goals, cost goals? You have a budget? You have a bottomless slush fund? Probably not, right? What are those goals? What are those limits to this work? You collect building data, talk to the project teams, talk to the people in existing buildings, look at existing utility bills, go to the site, really whatever means that you can. You're trying to collect all the information so you have a better idea of what's real. You build your energy model. You address your uncertainty either by calibrating in an existing building or by running those sensitivity analyses in a new building. You help facilitate design decisions, right? Whether it's an architect, working on a project with an engineer, whether it's a building owner who's just contracted you as a consultant, you kind of apply the same process to help them make decisions. And you help with validation. You clearly document your energy model, everything that went into it. So after the fact, somebody can come back and look at your model and true up what actually happened with what you predicted. A couple notes before we switch gears here and get into the case study. energy modeling, early and often, like they say with voting here in Chicago. Earlier on in the process, things are cheaper to fix, right? Like it's always easier to fix, change your mind before you bought it and it's arrived on site. Same thing in design. It's easier to change something earlier in the concept than it is at the end when everybody's rushing to meet a deadline. Couple of quick case study from a new construction project that we worked on, net zero project down in Virginia Beach. We noted a couple things, right? They knew they wanted to go net zero from the goal. That was a project goal, and they had kind of a tight budget, right? And everybody's talking about PV at the beginning, and kind of right off the bat, we were able to realize with the prices at the time that it was actually cheaper to add more insulation, right? We got the same bang for our buck as we did with photovoltaics. But adding 2-3 inches of insulation to the wall, that's not like a decision you can make like late in the game, right? That's something people need to know at the beginning because it impacts your wall dimensions and really everything else down from it. Same thing with triple pane, right? Like it changed your framing system, your wall system, but that too, it was actually more cost effective in terms of energy cost savings and payback to go with triple pane windows than with photovoltaics. So I just provide these two case studies because these are things that if you don't plan for them and get people to be like, all right, we're going to do this kind of early on in the process, it's never going to happen, right? So energy modeling needs to happen early and often. There are lots of softwares and available for this, right? Like I liken it to tools in a toolkit. I might have a saw, an axe, a scalpel, an X-Acto knife, all of these things. I wouldn't use the X-Acto knife to chop a tree. I wouldn't use the chainsaw to work on my balsa plane kit. So similarly, there's different tools that have different strengths to them. And one of the purposes today is for Ben and I to demonstrate 2 different tools and 2 different use cases for them. There's lots of resources available if you're curious about building energy modeling. ASHRAE Handbook of Fundamentals. There's ASHRAE standards for how you do this. There's standards for energy audits. There's an architect's guides for how to deal with energy modelers. Kind of weird people sometimes, on this forums, which are great. Tons and tons of resources. So before we get into our case study here, I want to ask, does anybody have an idea of just what the median Energy Star score is for a building in Chicago? Right, so remember 50 is the median. So is the typical building in Chicago better or worse? Worse than the median. 35. Okay. What about UIs? So the average building in Chicago is actually a little bit better than the average. I think we're like in the mid 50s. Office buildings are actually in the low 60s. There's definitely places where we're much better. But Chicago, actually, we have a lot of energy efficiency standards here. I mean, we actually should give ourselves a pat on the back. We are quite a bit better than the average building or than the average municipality. So I want to talk a little bit about a case study now. So we have an office in DC, not just the one upstairs. And in DC, they have a building performance standard. They rolled it out. So the way it is there, if you don't meet your, if you don't benchmark better than the Energy Star average for your building type, which for offices in DC, it's 71, right? So that's pretty efficient. DC office buildings are 71% of office buildings nationwide. And if you don't benchmark that, the penalty is $10 a square foot, right? Capped at $7.5 million, leviable every 5 years. The first fines hit people, I think, last month. So there's a lot of upset people. I cannot describe, cannot underestimate, what a shit show this was, right? Like when they announced this law, people sold buildings, freaked out, really made big market moving decisions, right? When you threaten fines like that, it's a big deal. And same thing, the owner of this building, approached us from that, not through a design team, we helped them with some other energy management stuff. And they're like, oh my God, we're facing these huge fines. What do we do? So we help them benchmark the building and help them identify this risk. So it's like a 62,000 square foot building in DC. It's 37% window to wall ratio, all electric, built in the 60s, pretty bad. So the site UI of the building, you can see there was 53, and that got an Energy Star score of 66. But the target is 71, right? So they need to get their EUI down to 49.7. So it's not net zero building, right? But they have a real performance target, right? They know what they're using now, and they need a path to get there. So the way that we did it was we looked for the reduction. We need to understand that, they need 7% reduction to meet the compliance, but we wanted to position them better for the future. The standards going to keep getting better if it compares you to the average. So we helped them set a 13% reduction target. We looked through all their documents. We interviewed tons of people working through the buildings. We visit tons of times within the site. And, we built an energy model and calibrated it until it matched the utility bills within 10%, ideally within 5%. We brainstorm things based on what we see on the energy model, and we ultimately work with contractors and cost estimating software to figure out like what makes a difference and which of it pays back quickly, and let's prioritize those measures. So just out of curiosity, where do you guys think most of the energy in a typical office building goes? Like in Chicago? Yeah, let's say Chicago. Yeah, that's true for actually the average building overall in the country and office buildings and every other kind. Yeah, definitely. So offices are more cooling dominated in some parts of the country, but in Chicago, we're still heat dominated. So I want to talk about how we use this software, what we use in this case, and the last 10 minutes to go through kind of a case study here. So for existing buildings, that service that we provide, usually it's called energy auditing. Some of you guys may have heard of it. And people view that as kind of a separate thing from energy modeling, but I don't, right? Like it's all the same thing, right? You're creating a model to predict how something works. So RETScreen is a energy modeling software really focused on energy audits. It's really good for audits where you have utility data. It's developed by Natural Resources Canada, which is the Canadian Department of Energy. It's widely used through the industry, various places in the US. So the reason that we picked this tool here, right, is it works on a monthly time step. It means it doesn't give you energy predictions for every hour or even every day, just once a month. Like that's not very accurate, you might say. Why would you do that? Because we only got monthly utility bills. Right? Like I didn't have really detailed, super granular smart meter data to work with here. I only had monthly utility bills, and I'm only going to get monthly utility bills. So, picking a monthly model is appropriate. The software models the interaction between ECMs. It provides a cost database, super handy. Be careful, pricing is crazy after COVID, as some of our friends in the manufacturer side might be able to tell. But, all these factors, monthly utility bills, interactions, somebody's going to do things over a course of time, it made RETScreen the appropriate choice. I really like it too, because there's like a ton of documentation available from it. It's a government product. There's like hours and hours and hours of like free YouTube training on it. It's really, really robust. It can do a lot of stuff, but today I want to just kind of go through that similar case study. So I'm going to switch gears here. If you guys have downloaded RETScreen software, please go ahead and pull it up on your computer, and we can go through this. I might sit down here. Okay. That's a little bit. We'll only spend about 10 minutes on this. Spend some time. Those interested in working through this will be able to cable? I'm sorry. Of liquid death. Yeah, sorry. Okay. Sorry, folks. A second here. Okay. So let me open my screen. Whoops. Did I lose something? Not sure.
Wi-Fi.
It's right there on the wall.
Did you have it just sharing one window chance?
I'm not sure why it's not appearing there though. Like it's like looks like the HDMI is not.
It looks like you're sharing a black screen with your border, your like border at the bottom.
Yeah.
We're back here.
Okay, great.
And I think you'll just have to reshare your screen.
Yep. Sorry for the technical difficulties, folks. All right, so for those of you who are following along here, so basically RETScreen is this tool for that allows us to energy model. It's not graphically based, so it's probably more friendly for engineers and not architects who like to visualize things. But it's useful for kind of a case study here. So when you're here, you guys can go ahead and open it. We're gonna go ahead and create a new file. So I've got a blank RETScreen file right here, and we're just gonna kind of start from scratch. So the first kind of important part, here is to define the location, right? So, as I said, this project is in Washington, DC, that we analyze. So if we wanna, sorry. My software popped up over here. So it'll pop up, you click set climate to location, this graph. Search for Washington, DC. You can say, it takes you right to the location and you can select, say, I'm gonna say, Dulles Airport, Reagan Airport. So this is, not average weather data. This is actually pulling data from, thank you. This is actually pulling data from NASA. So you kind of define the time period that you're looking at and it'll actually pull historical data and run it. So not average data, but real weather data. So once you got your climate data in, it'll set it, it'll show you all these kind of cool parameters about what your climate data looks like. And, we move on to our facility. So, when we set up our facility, we kind of want to define what it is. So, we talked about this being an office building, so office is kind of the choice. So we call it Northwest DC office building. And, we would enter our area. So let me see what that was here. So we were at 62,000 square feet, right?
Your minimum size of the building that makes this.
No, I mean, this process that I'm describing here is really it's useful for anybody, right? Like it's useful for anybody who has a building and really cares about reducing their energy performance or has some kind of real target, right? It always helps to have utility bills and say, here's where I'm at today, here's where I want to go. That's what this process is for, regardless of what it is, whether they want to decarbonize, whether they just want to shave it by 10%, it's the same process. So now we're here, right? And it kind of shows, and then we want to enter our building energy usage. So, we had in the US here, we're using kBTUs per ton, and the benchmark is the initial value. So kind of, the target that we wanted to get at, right, was an Energy Star score of 71. Right now, our initial, building that we're using had an Energy Star score of, I think, something like 42. So let's go ahead and put that in there. Just a second. Okay. So, our base case EUI, we were kind of quite a bit higher, right? Like we were at, I think, something like 53, 52. And then we want to set a target, right? So we had discussed that they wanted to have a target of minus 13%, right? So like when we have these all put in, right? So we end up having kind of the benchmark where we're at, what our base case is and kind of what the target that we want to set. This will carry throughout the rest of the analysis. So once we're here, we begin to actually build the energy model. So go ahead and click feasibility, right? And now we'll begin to actually enter the different properties. So underneath the energy tab, this is where we actually define how the building is used, right? So you can start by defining schedules, so kind of what are the space operating temperatures of your building. Let's say, in an office building, I'm typically going to heat it to say 70 degrees. In cooling, it's going to be 75 degrees. In unoccupied, kind of same thing. Maybe I'm taking it down a few more degrees. I can set the occupancy rate I can set the temperature outside when it changes over between heating and cooling. Let's say that happens when it's 55 degrees outside. And basically I can define how my building is operated. I also here have the opportunity to define specific factors about the building. So let's take a look and say, start with the energy tab, right? So let's start with the building envelope. The building envelope is the first thing that provides environmental separation. So let's think about what we have here. And a note on RETScreen, since it's kind of set up to evaluate efficiency options like proposed measures, you'll see wherever you go that there is an option to define both a base case as well as a proposed case. So, so let's say here that we're going to add a wall. All right, so our building has walls. Let's say, we can just kind of make up some numbers here as we go along. Let's see.
So I have a question.
Go ahead.
I mean, I'm not an engineer or anything, so that's what. So in your base case, you don't carry what your base initially is over to all of these areas?
So our base case represents what our utility bills are. It's what we're using right now.
I know, but so you have base cases blank. So do you carry that number to, like you said, 42%? Would you carry it over there?
It'll calculate it for me. So what we're going to do now is we're going to enter all these things about the building,
Okay.
right? Like the enclosure, the mechanical, the lighting systems, everything about how it's used, and it's going to give us a prediction on how it's used. And we'll get to that in just a second as well. So, the way that this would work is, I punch in the area. Let's say I have, 10,000 square foot of wall facing north. I'll say 5,000 of wall facing east. 10,000 again facing south and 5,000 facing west. We can define the R value of our wall. That's typically how insulation kind of is given. Let's say our wall, we have R values of 15 here. And then we have the option to define what the base case is, whatever's in our actual building. And also we can test kind of proposed improvement options. So every aspect of the building can be entered here, from walls to windows to doors to how leaky or tight your building is. Really all those things that impact your building energy efficiency. It's similar to, with lights. Like if we want to define like lights, we talk about for the floor area, how much lighting load there is per area, how many hours a day they run. Both the base and proposed cases, you can add costs for how much it costs to improve the proposed case. There's a really nice cost database here. Wherever you click through proposed measures, it'll kind of tell you, here's the average cost for different items. You'll see that really throughout, like even when we were back on the envelope side. Here, there's always this incremental cost tab for kind of estimating how much whatever you're trying to do is going to cost here. They have costs for additional insulation. They have costs for additional air tightness measures. So one of the reasons we love RETScreen, right, is not only does it help you calibrate the model, but it also helps you kind of get a sense of what these things that you're proposing are going to cost. So you would go through this entire process, right, really defining kind of in detail all of these different things, whatever's in your building, ventilation fans, electrical equipment, hot water heaters, pumps, fans, motors, really anything you can basically imagine, even compressed air, anything that's an energy user is going to be available in RETScreen. And you would go through this similar process, and we did for this building, of understand what's there and then build a model to kind of match it. So I provided a link on the Google. Does everybody have, was the Google Drive shared with everybody here?
No, not yet.
Okay, all right, then I have just a second, a link right here that nobody can see because I'm not sharing this. Just give me 1 second. All right, oh my God. All right, so there's a link right up here where I've got the model file completed. So I've actually shared the actual model file we used for this real building to play around with it. So here we've actually gone through and entered the walls, the roofs, the windows, everything kind of consistent with what was in that building. And this is what we used to assess it. So I'm going to spend just 5 minutes walking you through how we did that process with the built model, and we'll close it out. So I'm back here in this model here. You can see that we've set up all of our facility parameters, 61,855 feet to be exact. We've defined all of these different parameters, walls. There's even an EV charger here that we put in to account for its energy usage, fan coils, hot water system, pumps, you name it. I mean, I think there was even a solar hot water heater for the pool. But, General Motors, really anything that was involved there, we really went through, kind of understood what was there and made our best guess at what it was.
How'd you get all that info, drawings or site visit or both?
Both, yeah. So this was an existing building with an owner who we know. So we were doing an energy audit. So we went, spent a whole day, walked around the building, took photos of everything.
One day.
Yeah, digging. We spent one day at walking around the site, maybe about a half a day digging through random old drawings from 1968 in the building engineer's basement. And then like tons and tons of service records, interviews with folks. It's split between drawing reviews and whatnot. So actually, this is our completed model here. So I wanted to actually find a curious one lesson at the beginning. So I'm at the window section here, right? So building envelope where we've defined our windows. So the building actually has pretty good windows, right? They had a U factor of 0.445, not amazing, but not terrible. At the beginning, we didn't realize that they had been replaced, so we thought they were a lot worse. Right? This is what we assumed. This is actually the ASHRAE recommended value for existing unlabeled fenestration. Right? We didn't know when they'd been replaced, so we kind of started out with that. So after we entered all of our information in here, and we also entered all of our utility data in here on the data side, right? So we actually put in all of our utility bills. We were able to make a comparison between the two. So if you come to this project, come down to the summary slide and take a look at the comparison, we're able to see the base case and the proposed case, right? Like how it's compared. So right now, I haven't included, so we have a couple of the measures here, right? Looks like it made some bit of difference. So what we'll do is let's see what happens with nothing. I just click the include measure button and uncheck this. So all of these proposed measures that we considered are now going to disappear, right? Gone. So when I come back.
Ajit, are you able to select the type of wall insulation and stud types used?
It's a great question. So let's take a look. You can actually build your walls like line by line, the same way you can in any other energy modeling software, and it'll compute the overall R value for you. Or if you've already done that yourself, you can simply put it in yourself. But RETScreen has all the calculators in the back end to help you kind of figure these things out as well, too. So great question, thanks. So yeah, you can see here, like, for our building envelope, we were considering, in this case, I'm assuming that we had a U value of 0.95 before, our proposal is to improve it. So, coming back to the comparison here, to kind of see, so when I removed all of our measures, we're not proposing any changes. After renovation, we're going to be the exact same. When we built the energy model and we compared it to our historical consumption, we were actually off by about 15%, right? We couldn't for the life of us figure out why we were 15% off. And it actually turned out to be that thing with the windows, right? Like where they replaced them recently, and they were able to share with us like what those window values actually were. And that's why we know it so specifically, because we had a cut sheet. And when we did that, and kind of came back here to the comparison, like we were now within 1% of our energy usage. So this process is called calibration, right? You take your first guess at what you see, and you're inevitably not going to be 100% right. And you keep doing research and trying to identify those gaps until you can close it to a reasonable extent. Then once you're at that, it's kind of important to see like, where's my energy use going? So if you click, I click the end use button up here, it'll show you kind of where this building is breaking down, right? And we saw that space heating, mechanical equipment like fans and pumps, lighting, all of these it's a pretty even split. But we started to look at the larger end users, heating and cooling, to see, where we can make some savings. And so, with our experience as engineers, talking with the project, trying to understand, what all kind of makes sense, we developed a list of efficiency measures, things like, improving the chiller, improving the envelope, improving, various items. And all of these are, again, defined here, like in the energy tab. So for example, if we were looking, let's talk about the chiller. Oops. Somewhere, cooling, sorry, here. If you look underneath the chiller, there was an existing train, 140-ton chiller, right? And like, so here we are including like an upgrade for it, but if we wanted to test an upgrade, we could try a new value here. So back to the measures. What we did is, let's see what happens if we include everything, right? Every idea that we came up with. Let's see, like, what that would do. Give it a second. All right, I'm sorry, I thought this file had these preloaded, but let's just for demonstration, give it an example. All right, let's say that we're going to replace our windows, right, with a factor of down to 0.3. Right, and let's say, what would that cost? Replacing our windows, would cost a total of about, fixed price average, about $215, per window on average. So we could enter that in there, right? It'll automatically pull out what our cost is based on our square foot of window. We come back to our include measures tab. We note that we have now a measure on the building envelope, right? It saves us this much heating, this much cooling, adds this much cost, this much fuel savings, and has a beautiful, attractive payback of 42 years, right? So not exactly ideal here. And I'm sorry, if you folks can just bear with me for 1 second. I'm gonna try one more thing here.
So typically, I mean, this is the question is, I'm trying to learn this. So a simple payback would be less than 10 years or?
Depends on the owner. I mean, if somebody is like a university and is gonna build it and own it for the next 100 years, it might be 25 years.
Yeah, I mean, so if it wasn't a school or something like that.
I work with hotel owners that buy distressed properties and renovate them and flip them, right? So their acceptable payback is 3 years, because they're never gonna hold it for more.
So it just depends on the.
It really depends on like where you're at, yeah.
Okay.
So. Okay, sorry about the technical difficulties, and Ben, I'm sorry for chewing into your time, but I'm almost done here. So. The wrong version of this file on here, I'm sorry, team. So basically the idea here is you can enter all of these different values. You can stack them up by payback. And typically the idea is to prioritize those that have the highest impact, that payback in an acceptable time. Usually there's also limits to what you're willing to cost, like this costs $200,000. So even if it didn't pay back, it might just be too much money. So typically the process involves working with the owner to identify all those things that pay back quickly, do them up front, and those things that cost a lot but still have an attractive payback, you kind of advocate for the ones that make sense. Here in this project, actually, it did make sense to replace the chiller, right? The chiller was R22, old refrigerant, not available anymore. So even though it had a longer payback, they were like, let's do it. I'm sorry, I'll also post a version of this that has all of those files here. I'm not really quite sure like why that wasn't there, but I'll walk through you guys, through the activity. But really that process with RETScreen involves putting in measures, including the ones that make sense. There's this really nice target feature there where you can like create, different targets for the baseline, base and proposed cases. You can add filters that filter things by simple payback, only things that pay back. only things that don't cost more than a certain amount. So you can kind of filter it to only include, those measures that make sense for you. So going through this process here, we were able to come up with like a ton of different measures. So these are the ones that paid back. We noticed a bunch that paid back right away. Some that, cost little, some that cost a lot. But we were ultimately able to land on the set of measures that met the owner's payback criteria, that met the owner's budget for first costs, and ultimately led to a 16% energy reduction. So they were targeting 13%, and we were able to achieve 16% through this process. The things that helped us do it were choosing the right tool, making sure to get familiar with the building, and looking at historical utility data. So ultimately, this process of performance modeling can be applied to any existing building, whatever the goal, whatever the size, it's the same approach. So we'll have an opportunity to work on that during the exercise portion, but I'm way overdue to hand this back to my colleague. So please, Ben, go ahead.
All right. Do you have a mouse attached to that already?
Right here.
This is, okay, but is that one functional as well?
Yeah.
Okay, cool.
Hey, Ajit, while we're transitioning to questions from the chat here, what kind of data is being used within RETScreen for HVAC energy estimation? Is that manufacturer's data or data?
Great question. So in RETScreen, you input things like type of equipment, the capacity of the equipment, the rated efficiency of the equipment, and RETScreen has engineering calculations built into it. So if you're like, hey, here's my building, here's the envelope, it'll estimate what the heating load is. It'll take the properties of the equipment you've defined to predict how much energy it's using.
And does the tool have any standard factors for cost and payback that could be used at a pre-modeling level?
Yeah, it has all a cost database built in. It's just important to be familiar with your local market and escalate it appropriately because costs aren't the same in Hawaii as they are in Texas. Right.
Hi. How's everyone doing? Good? All right. Okay, well, believe it or not, this is about as exciting as energy modeling presentations get. This is good. We're doing great. Everyone have fun. All right. Yeah. Okay, so this is my kid. I like this picture for 3 reasons. Most importantly, it reminds me why we do any of this, right? Like climate change is the biggest problem facing humanity, probably, or one of the biggest, and we want to leave a better world for our kids, right? So that's why we're doing what we're doing. I love this t-shirt. The context within energy modeling is that, we know how to build energy efficient buildings. We know how to build zero energy buildings. We have heat pumps, we have solar panels, we have all the science and technology that we need to do this. We don't have is the will, political will, the economic structures and the design practices and habits to actually make this happen. We have all the parts. We just need to put them together. And she's really excited about her new shoes, and I'm really excited about shoebox modeling. So that's why I like this picture. Okay, so oh wow, these colors are bizarre here. Something happened. I'm sorry. White on yellow is awful. Okay, we're gonna muddle through this anyway because I'm not gonna fix this. Anyway, I'm not gonna read through all these, but good energy consultant, knows the tools, works quickly, is responsive to needs, answers questions. That's your job. I've been doing energy consulting for 15 years. It's very important, but what I realized was the problem is that people weren't really asking me the right questions. They weren't asking me good questions. They were asking me dumb questions. Like if I have this little 4-inch fin and I attach it to my glazing assembly and it shades a little bit, is that going to improve my building performance? And then, I'd run all these simulations and these detailed models. And after doing that for a long time, I could pretty much tell everyone what the answer was right away. Yeah, it's going to save you about 0.5% energy, plus or minus 5%, because I'm not sure what kind of thermal bridging you're introducing into your window assembly when you do that, right? So that got to be a little tedious. And what I realized is that people weren't asking me the really big questions, like what building systems, what energy efficiency measures really have a big impact on this building? Like what is important in the whole design space, not just within, the narrow focus of the architectural glazing assembly or, the heat pump chiller controls. Like those details are important, but what's really important is focusing our design efforts on the activities that actually make a difference in the project, right? Like we all have limited design fees, limited time to do the jobs that we need to do. We need a way to focus in on what really matters. We need bad ideas to fail fast, and we need to be able to focus on the good ideas. So that's what this is about. Really understanding the building, helping our clients ask the right questions and answer those questions in, what I would consider like quasi real time. No one has time to wait 2 weeks, 4 weeks for an energy model to make decisions. They want to make decisions now and keep moving. So we need to be able to support that. This is where great ideas happen. Great ideas happen in the sketch phase, in this hand sketch phase. I mean, architects still do this. They sit around offices and whiteboards and there's scraps of translucent paper and draw stuff and have ideas, and they need feedback on what's happening. This is just one example of that. This is a project where they're building a new like brewery, bar area. We actually figured out that they could save a lot of energy by making this one building into 2 separate buildings. And it had energy benefits because you have fewer square feet of conditioned space to actually work with. But it also had other practical benefits too, like 2 smaller buildings had, fewer like fire code and safety regulations that they had to comply with. So you can come up with these really cool ideas that save energy in this kind of sketch phase if you have the tools to support that process. And Ajit beat me to the tool analogy already, but these are my tools. There's lots of different energy modeling tools out there. They have different strengths, different weaknesses, and you're never going to get through a whole project using one tool. It's just not practical, just like you wouldn't build anything starting from a tree into a piece of furniture with one tool either. It's not practical. So you have to be okay with learning tools and understanding their strengths and weaknesses. Here is, concept models have come a long way. I used to work with a guy who in college was doing energy modeling with punch cards, feeding them into a computer and running Fortran. And then, I've worked with other people that used to do energy modeling like in the 80s and, command line codes. And, I spent my career, learning the depths of eQuest and IESVE and can spend a lot of time in a lot of those details. But again, concept models need to be fast. They need to be responsive to what's happening now. We've actually developed an in-house modeling tool called Sketchbox that makes this initial concept modeling phase much faster and allows us to just apply modeling in more circumstances. There's this idea in the industry now. So, most projects will have a concept model. Hopefully they'll have a concept model. At some point, someone's going to need to build a more detailed model, if nothing else, to get good HVAC loads, right? To size your air handlers, to size your heat pumps, whatever it is that's happening in the building. The mechanical engineer needs a detailed model, room by room, zone by zone, to size that equipment. So there's going to be a second model in there, probably 2. And then sometimes that model can be translated into something like a code compliance model or a lead model, but oftentimes that ends up being a third model. Maybe the loads are done in train trace, but then the lead model is done in eQuest or IES. So a lot of times there's multiple models on any given project. Sometimes when you're working in an area with like stretch code and lead requirements and other things, you could have like 3 or 4 models of the same building before you get all the way through the design process. There's this idea in the industry now where SPRM means Simplified Performance Rating Method. So there is a movement out there to take what's great about concept models and carry that through to codes and standards and compliance modeling. not going to dwell on that, but that is a thing that's out there that you can learn more about, and that will save the industry a lot of time if we're able to kind of move towards that for not every building, but maybe smaller, simpler projects. Okay, so yeah, we're missing a few things here, but Sketchbox. So I mentioned we created our own energy modeling tool. It's built on the Do2 or eQuest platform. We originally built this just to be better energy consultants. My firm, Slipstream, runs the ComEd energy efficiency program. So we do hundreds of models every year to support that program. And we just needed a way to work more efficiently. So we created this model just to be better at our job. And a few years ago, realized that it had gotten to the point where it was really worth sharing with the world because it's cool and it works really well as a concept energy model. So Sketchbox.io, there's a free version that costs nothing. There's a low-cost version that's, I think, $149 per year that you can expense to your employer if you're interested in getting a few more features. But again, like order of magnitude cheaper than everything else that's out there. So I encourage you to check it out. But the design requirements to this are really simple. So we want it to be accessible. We want to expand the user base of people who are using models for design, model-based design decisions. Part of that is, minimizing the jargon that goes into that. I mean, you could talk about the jargon for days, like what OS, ERV you want to specify, right? Like trying to get rid of all that stuff so it's easier to learn. Has an intuitive workflow, works on a phone, a tablet without any kind of dedicated software or licensing. We want this to be robust. So like one of the big problems with energy models is that they crash, right? You spend hours and hours putting in all of your inputs, and then you get all these horrible bugs. Energy model won't run because some like data point isn't, it's like 1 millimeter away from some other data point because you snapped to the wrong thing in the PDF or whatever. So trying to get rid of all those errors so that it actually runs on the first try, doesn't break, doesn't throw errors. And then the results are kind of pre-validated. So if, in a traditional energy modeling tool, the more power, the more flexibility you have, the more opportunity there is for errors and getting like junk results out. So we've tried to kind of pre-quality control all the inputs so that you really can't get a terrible answer. You're going to get a pretty good answer every time. So in any case, yeah, it's fast. So that's the main thing. It doesn't give you perfect answers. It doesn't represent 100% of all the building systems you're going to see out there. It doesn't give you total flexibility, but it gives you pretty good answers quickly, which is what you need to be a good energy consultant early in design. Well, I'll go through a demo, so we don't have to go through the whole workflow, but there is kind of a standard workflow. And this is the results that we get. So we do some post-processing on this results too, present it visually so that you can make, the visual part of our brain is so powerful. Like we can see immediately which of these measures are critical measures for the building, which are maybe not worth looking into. And they're different. And this is the great part about energy modeling, right? This is a hairy, complex, multi-dimensional design space that we're trying to intuit and understand with our brains. And that's why these kinds of tools really help, because we've got two different projects, very different, results in terms of what matters in these designs. So this first one on the left, this is a new elementary school in Massachusetts. And this is about what I expect to see for a new building. Air sealing is really important. Triple pane glazing is really important. Lighting, power density, miscellaneous equipment power. Those are the big hitters in new construction buildings. So not just building to code, but building beyond code, where are the big opportunities to save additional money? Very different than this reuse historic courthouse jail in Illinois. They're turning this into a restaurant, brewery, event space thing. The best measure by far was blowing some cellulose into the uninsulated roof. Like that blew everything else away, right? Like, so you wouldn't necessarily know that about these two projects without going through this process of doing like a concept model. Again, like maybe this isn't the perfect answer, or it's not going to predict exactly how much money someone's going to save, but it focuses our attention on the right things.
What's task tuning?
There'll be a high-end trim of the lighting fixtures. All right, so you install, let's say, well, these are maybe T8s, but you know, modern LEDs are all dimmable. You have only so many fixture selections for a space, right? Like you've got your ceiling grid, you want to meet 30-foot candles. Maybe this design has, you know, LED fixtures. You can select from 3 different power outputs. You choose the middle one, but your space is still a little bit overlit, right? Maybe you're at 40-foot candles and you don't really need that much. So task tuning is the second step of going into that control system and saying, all right, the power output doesn't need to be 100%. It can be 87%. And then you're hitting exactly 30-foot candles with your light fixtures, and you save quite a bit of energy.
It's important that you specify that the lighting contractor should actually do that.
Exactly.
If you're gonna model it, it's gotta be in the document somewhere.
Absolutely. It's essentially a free measure these days, but it's got to be in someone's scope of work. Okay, so I'll just touch on this briefly, but like I said, we run ComEd's new construction program. ComEd has dozens of different energy efficiency programs, but if you're working on a new building or a major renovation, not only can you work with free energy modeling tools from Slipstream, but we can actually pay you to use them too. So this is a couple of our program offerings. We have what's called best practices, which is for warehouse, office, retail, multifamily, parking garage. We have like these preset groups of measures, and we've used our modeling tools in this case to kind of pre-calculate what the savings opportunity is for these types of buildings. We put together like low-cost, practical, beyond code improvements to those buildings, and we're offering dollars per square foot incentives for meeting those requirements in a new construction building. So that's kind of one offering that tends to work really well for like private developer-led projects, the really fast-moving, spec offices, distribution warehouses, retail stores, that kind of thing. So those kinds of projects have fit really well there. We also have a more of a performance offering, which is much more flexible. You're doing like a high school, a hospital, a university building, anything maybe with a longer design timeline, more aggressive, energy performance goals. We have a fully flexible program offering too that works well there. You don't have to go for these, but there's an owner incentive. So whoever pays the utility bills at that property, the building owner, the building developer, they get an incentive, but also the design team gets an incentive. So if you're an energy modeling practitioner, you work for a mechanical engineering firm, electrical engineering firm, architecture firm, you are eligible to receive these design incentives. There's kind of a la carte, but so if you go for a rating system like LEED, for example, you can get $5,000. If you design for an all-electric building or electric-ready building, you get $10,000. Again, these go to the design team. And if you use our energy modeling tools and help us turn that into an incentive offer for the owner, you get $5,000 plus 5% of the owner's incentive, or an additional 5%. So again, some projects are getting, $20,000, $30,000 for going through this process. And that's exciting because you can pay a junior engineer for a week to draw up new details and rewrite your specs and do all this stuff to kind of advance your design practices without having to charge the owner for that.
I just $10K is like market value. $2 bottle.
Yeah. Absolutely. Okay, so I'm going to get into the tool to do that.
While he's loading that up, I'll also point out that other jurisdictions have similar incentives. Like north of the Cheddar Curtain in Wisconsin, there's Focus on Energy. And they have a similar program where you model and submit it, and they actually pay the energy modeler with stipend. It's only $1,500. I'm not quite really generous, but there are incentives. It's not just here, ComEd in Chicago. It's wrong.
Is there a trick for getting this mouse to work? Oh, this one. There we go.
Might be able to duplicate the screen so that you don't have to like look backwards.
Yeah, that'd be nice. Okay.
Windows P.
Okay. Well, while I'm getting this set up, was everyone able to get to sketchbox.io and create accounts? Anyone have trouble with that? Okay.
While you're setting up, are you able to answer a virtual question?
Sure.
What are the main differences between Sketchbox Basic and Standard?
Main differences are Sketchbox Basic gives you just 2 shelves to work with, or 2 building design components. Standard allows you to do much more. I forget what the upper limit is. And the other difference at this point is that the standard subscription allows you to download all the native eQuest files, which then you can open up in the free eQuest tool and poke around under the hood and understand all the assumptions and inputs. As we release more features, we'll probably be releasing them primarily to the standard version as well. Okay, let's see. What'd you say?
Windows P.
Windows P. It says screen sharing has stopped, so I'll need to do that again.
Then you don't have a model to share with people, right?
I don't, no, we're just gonna go from here. Okay. Try to hide some of this stuff so we have more real estate. Okay. All right, can everyone still see and hear okay? All good? Okay. So a little bit of cutoff happening on the projector, but I think we'll be fine. Okay, so I guess some of the initial things for Sketchbox is this is a website, so you don't need to install anything. We do have some support, so some of you that maybe are already modelers or might be familiar with this unmet hours forum. So a lot of different tools are represented there, and we have a Sketchbox hashtag where a lot of questions have been answered, and you can post new questions. If you have more administrative things, there's like a little support button there that sends us emails, and we can get in touch with you. We do have some very basic documentation as well, if you want to like understand a little bit more. Another important thing is there are 2 ways to save a project. You can save a project to your cloud account, so only you that's logged in can see that project and reload it. So there's no like native on the cloud sharing functionality, but you can download a file. That file is called this .json that you can send to anyone, and then they can load that up, and then you can share projects that way. Similarly, there's two ways to load a project: from your list or from a file. Okay, so yeah, a few little administrative things there. One of the powerful things about this tool is that we try to provide you with the best defaults that we possibly can. Some energy modeling tools give you really terrible defaults, which is another strategy because it forces you to think about every single input and do your research. So, but that doesn't jive with the need for speed. So we try to give you the best defaults that we can. These values that are in blue text means that it's a value that's being looked up based on something else. So this is a good example: cost of electricity. It's based on location. If I choose a location that I know has much different electricity values, we'll see that change. So 25 cents kilowatt hour instead of 11 or whatever. You can overwrite these. So if you know that your cost is 15 cents a kilowatt hour, you can put that in. That breaks that link. So if I go back to Chicago, it's still 15 cents. If I want to restore that link, I can do that. So you'll see that throughout the tool. one of the nice things just off the bat too is that we have a lot of the energy codes built right in. So, ICC 2021 is the current code for Illinois. Within that code, we don't have every single variation of different compliance pathways, but we have some of the most common or most important ones, right? So, maybe you're interested in complying through ICC through the ASHRAE 2019 pathway. So we'll see where that information goes in just a minute. There is kind of a linear workflow through these tabs, which helps navigate. So again, this is a shoebox model. We're building really basic things. They're boxes, rectangles, but you can do quite a bit with this. So I'm just going to build out a really simple example that might be something that you'd see here. So we'll do like a little mixed use tower, which is something that we see around Chicago quite a bit. So we have control over the area. So let's call this 20,000 square feet. The aspect ratio, which is just the width divided by the length, we'll make that 1.5. You can control the number of floors, the floor to floor height, some other parameters here. You can specify the glazing, by facade, and again, have a little bit of visual feedback to understand that, what you're doing is what you want. And again, right now we're building the baseline building, which might be, if you're in new construction, this is the building that is the minimum legal building that you can build. If you're starting with an existing building, you'd be trying to match the parameters of your existing building, right? You can have skylights if you want, although it's not appropriate for this example. And then you have some control over HVAC system. So let's see, for this one, let's choose an electric heating fuel, and maybe this retail has VRF units. So there's our retail component, but then we can add more things. Maybe there's, on top of this retail, maybe there's a parking garage, so we can select that. Let's call that 40,000 square feet over 2 floors. Again, aspect ratio 1.5. And so I have some decisions here. I could keep those as separate buildings on a campus. I can connect them, using the right click interface here. I can connect them that way. I can stack them on top of each other, which is what I'm going to do here. So we've got 1 floor retail, 2 floors of parking. Let's add one more thing. Let's add a hotel. Maybe 140,000 square feet. Aspect ratio 2. All right, 10 floors. Sounds good. All right, so I'm going to attach that here. Okay, so once upon a time, this would have taken me like 20 hours to get to this point in older energy modeling tools. So this is fun, and we can keep going. So this, for the parking garage, I'm going to just say heating only, natural gas. For the hotel, let's say packaged heat pumps. Oh, let's do electricity. Packaged heat pumps. We'll do water source heat pumps. That's a pretty common hotel system type. And then you also have the option to choose a dedicated outside air system if you want. So none means that you're bringing outside air in through that primary heating cooling system that you selected. If you choose a rooftop unit, that's going to add a gas-fired, DX-cooled, dedicated outside air unit that's supplying all the ventilation air for the building. If you choose same as primary HVAC system, it's going to turn that DOAS unit into the closest match to what your other system is. So in this case, that'd be a water source heat pump. If you had a ground source heat pump, that'd be a ground source heat pump DOAS. If you had a gas-fired VAV system, it'd be a gas-fired VAV type DOAS. But in this case, let's just choose rooftop units. That seems like the practical choice. And for domestic hot water, we're going to say natural gas too for a hotel. Okay. Site offers a few other things here. Number one is the ability to change the orientation. You know, if I change that value, that changes the, you know, the compass position on there, so you can orient your building in different ways. Also the area of parking lots, you know, maybe this is an urban setting, so we don't really have any, but this just sets the values for like any exterior lighting that would be on site for parking and driveways. So moving on to schedules, by default, we're loading up like ASHRAE handbook, occupancy schedules, lighting schedules, hot water production, plug loads. So if you're happy with these values, like for a hotel, you can just use those. If you know that, you know, I don't know, maybe retail is a better example of this. So this would be a typical retail schedule according to ASHRAE. But if you know that, you know, these stores have a specific schedule, you can specify that here also using the simplified schedule. So maybe this particular store is open, you know, 6 a.m. to 11 p.m. It's open late. So you can do that. We give you a little bit of control here over like the mins and maxes of those schedules. So you can play with that. Again, if you're working on a new building, probably ASHRAE is a good choice. If you're working on an existing project and you really want to get into the details of how it's operating, you can do that.
How did you stack them?
Sure, yeah. Just going back to the design here. If you right click on any surface, you get a little menu. That's one way to do it. That's the easy way to do it. There's also this concept of parent shell, parent child adjacency. So like if I select here, so this parking garage, its parent shell is retail and its adjacency is above. So you can also change that kind of manually too. But the right click is, I think, more intuitive.
Could you quickly define aspect ratio?
Yeah, I mentioned that. That's just like the length divided by the width. So if you have a building that's oriented this way, that would have a positive, you know, greater than 1. If I change that to 0.75, you know, that turns it the other way. So that's how long and skinny is your building compared to square. This is the part of energy modeling that really takes the most judgment. And this is where people maybe start to get into trouble, right? Like we're trying to build simple models. We're not trying to make these things complicated. So when you have, you know, a building that maybe like steps back a little bit as you go up in the number of floors, or maybe you've got a partial basement that's kind of unfinished, like inactive storage and mechanical rooms, like, do I try to model that? Do I ignore it? You know, if I've got a complicated roof line or facade details that have like lots of little bump outs, in general, you just kind of want to blow over that stuff. What's important is to get the square feet right. You want to get approximately the right exterior surface area. So if you've got some weird shaped building, U shapes, L shapes, you can do that by like, you know, putting some different shells together in some different orientations. But for the most part, if you've got your floor area right, your exterior surface area approximately right, and you've got your sort of window glass exposures approximately right, you're going to be in good shape. You want to keep it simple. Again, you also don't want to be thinking about this in terms of like individual rooms. You know, we have the concept of a hotel in here. That's going to include lots of different area types, right? There's kitchens, there's dining rooms, there's the actual hotel units, there's corridors. We don't want to model those all as separate programs, separate shells. You know, all that stuff is kind of bulk included in this hotel. And then we lose the granularity of knowing that there's a ballroom in there with its own schedule and its own temperature set points and its own occupancy profiles, right? Like we lose that granularity, but that's what we sacrifice for the speed of having these like high level building decisions that we can make. So that's where you graduate into a more detailed energy modeling tool at some point in the design process. Yeah.
So I noted that you still had like parking garage, a hotel, which are 2 different use types. So
Right.
what's your like kind of yardstick for determining when, okay, like a ballroom would be part of a hotel, parking garage is something. What's your perspective?
So yeah, one way to answer that question is, it should be big enough components of the building where they have multiple thermal zones. So what's a thermal zone? It'd be like, in a typical building, like the way we're modeling this, you've got a core zone, which represent all the parts of the building that don't have exterior wall exposure. And then you have four, north, south, east, west perimeter zones that each have their own thermostat, their own, mechanical systems attached to that are separately controlled. If you don't have multiple separately controlled thermal zones of a space, it should not be its own model, right? Like some people try to model a corridor as its own thing, like stick it inside here. That's not probably the best thing to do. Or some people try to stick a conference room in there or something. That's not. But if you've got a gymnasium attached to a school, that could be its own model. Certainly a parking garage, anything that's just very different, but also large enough to have multiple thermal zones. Does that make sense? All right, let's keep going. So we talked about schedules, moving on to baseline. So if you're building a new building, which let's assume we are in this example, this is where all of that code information from your home screen will start to populate values. So this is the roof value that you need to achieve legally for a hotel, under ICC 2021. So that's going to have envelope properties, glazing properties, lighting power densities, lighting control requirements will be in here. Mechanical systems, what is the efficiency of our heating and cooling equipment? There's some things here that are not code regulated. Big one is miscellaneous equipment power. So we've pulled this value just based on our judgment from other sources. So not everything is coming from code, but we've tried to provide you with good starting points for all this stuff. Infiltration, that's a big one. That's starting to become code regulated, especially for like individual assemblies of things. But in general, this is a big unknown with energy models. Like how leaky is this building? 0.6 air changes per hour. That's probably pretty decent assumption for a new building. If you're working with an old building, I've seen this as high as like 3, 5 air changes an hour for a very leaky building, right? And I've also seen new buildings with much lower values if the contractors, designers spend the time to try to achieve that.
Overblower or infiltration as an air sealing measure, you better specify a blower or a test afterwards.
Absolutely, absolutely.
Look, passive house will show up there.
0.06 CFM per square foot at a 50 Pascal.
Yeah.
This is probably just at like wind conditions, right?
Yeah, so this air change per hour will get modulated by the model based on the wind from the weather file, but you do have to convert. So it's a different way of measuring, right? So you need to first understand your exterior surface area and then apply that. So it's a different way to represent that number, but it's the same idea.
Actually, the German passive house criteria is 0.6 air changes an hour,
Yeah.
but not under normal conditions. It's when you
Under the
pressurize.
test condition.
So like, just because it says 0.6 here, it's not as stringent as like a passive house.
Correct. Yeah. So that's one of the big, kind of unknowns in a model. And I think, people are just getting into this, spend a lot of time trying to get the geometry exactly right on their energy models because, especially for engineers and other technical people, there's a right answer, right? To draw every single part of the facade. But then you get to things like this, and there is no right answer for what your infiltration number is. So this is where you start to you have to develop some model judgment on which values are important to spend a lot of time on, which values you can kind of move past.
A follow-up question. So you obviously have many years of experience. You have like a sixth sense for this. But how would somebody who's starting off and doesn't know like what is important or not, how would they kind of develop this judgment for like what matters and what doesn't?
Yeah, well, I mean, I guess one answer is we've tried to build a lot of that judgment into this tool. So this is a good tool to learn on and get started with. And then I guess the other answer to that is, doing sensitivity analysis, right? Like I'll show you how to start to model trees. So one of those things might be, demand control ventilation. That's required for some spaces and some buildings. You have to make a judgment call here on, is that required for your entire hotel or not, right? Like, so you have to make those kinds of decisions on this page, and you can't necessarily look that up in the code. It requires a little bit of judgment. Same with energy recovery here. Like, the energy recovery is required in a lot of cases, but there's a lot of exceptions. So here, again, you need to make a judgment call on whether that should be in your baseline. I'm going to say yes, it is here in the case of a hotel, because we've got a lot of outside air coming in to replace that toilet exhaust. I'm also going to turn off daylight controls for the hotel. Those are going to be required in the common areas of the hotel and, offices, ballrooms, stuff like that, but that's typically not something we'd see in the hotel units, which are on the perimeter of the building. So I'm going to turn daylight off here. So these are just a couple examples of modifying the baseline based on, some good judgment about what's happening in this building. This is also where, if you're working with an existing building, the code value isn't the right value for your baseline. So you'd want to come in here and modify this. Maybe that wall U value is 0.35 instead of 0.055. So you can do that. This is also how you'd represent building types that are not in this list. There's not everything is in here, right? So if you had a laboratory, a house of worship, something like that, you'd pick the closest starting point and then come into this baseline tab and start to modify that to reflect what's actually happening in your building. So I made a couple of changes here, but in general, these are good defaults for what we're talking about. There's a few things here on the site related to exterior lighting. We can kind of just blow by that for now. That gets us to the exciting part of starting to define measures. But before I do that, I'm just going to go to the results. If you happen to hit this tool at a time when no one else is using it, you might have to wait like a minute or two for those servers to come online and start generating results. But once everything's warmed up, you usually get results in a few seconds or like a minute. So it's very fast. If we go down to this chart, so again, if you had an existing building and you had electricity bills or natural gas bills, this is where you could start to calibrate. Same as Ajit was talking about, you can start to calibrate this model to what you have from your monthly bills. So you could try to start to line these up to the information that you have and start making some calibrations. And if you're off by some amount, I would go back to in this infiltration factor, this miscellaneous equipment power, maybe ventilation rates are not exactly known. So you can start to play with some of these big driving parameters to try to start to close that gap between the model and the information that you have. So that's
How do you just categorize uncertainty, right? Like, a lot of us are familiar with it, but like, how would you kind of arrive and say which of these should I start with?
Yeah, so that requires a bit of judgment. We're working on some possible tools to help users do that and identify. We have the power of cloud computing here too, so we haven't fully leveraged that in this tool yet, but I hope to someday have a little utility that says, enter your bill data, and then the model will run some automatic permutations to try to match what's there. But for now, that's kind of a manual process. But
I would toss in that anything that depends on how the occupants are going to use it.
Absolutely. Schedules are big. Infiltration's big. Miscellaneous equipment power is big. Sometimes like heating and cooling efficiencies are drastically different than what a nameplate might say, especially if it's older equipment. Yeah, I mean, those are the big ones. But yeah.
So on this model, I wanted to use it for an existing older home.
Mm-hmm.
When I look at, when I put in information for all the utility bills and then go back and try to, or how would I start that? So
Yeah.
for instance, yeah, I have a house.
Yeah.
And I want to make it electric.
Sure. Okay, so unpack that a little bit. The question is how, if you want to try to calibrate your model, like for a house, where would you start? So at the moment, we don't have an ability to put in utility bill information. So RETScreen does have that ability. We're planning on doing that at some point here too, but right now you just have to look manually at what the model outputs say. So this is electricity, this is gas, and you try to match that up to what you have. So that you might be working in a side spreadsheet or something like that at the moment to make.
So if I look at your model
Mhm.
and I look at just say I look at my electric bill and
Yeah.
I want to change it to, because I'm using gas and I want to change it to electric. How do I know what numbers to put in there to kind of see how that changed when you change the graph from electric versus natural gas or anything like that?
Okay.
Is that one?
Yeah, so we're not changing systems here. What we're doing is trying to match this. These are the outputs of the model that we've currently built, right? So if I am looking at my gas bill and I see that for this building, my gas bill in January is actually 12,000 therms instead of 9,000 therms. I can come back to my baseline and say, well, let's just increase infiltration and see what happens, right? So
that would be the field that I would change for it.
that'd be one field,
Okay.
right? So what we're trying to do right now is get a good sense of where, what our inputs should be for the building that exists now. And in this case, I blew way past my 12,000
Oh, you would. Yeah,
therm
because
target,
it's-
right? So we'll try to hone in on, what that really is.
Yeah,
And
those things that you kind of guessed, right? If you make a model and
Yeah.
it doesn't match your utility bills, something that you guessed wasn't right.
Utility bill's supposed to be wrong.
Yeah,
Well,
yeah.
yeah, but I mean,
That can happen too sometimes.
Yeah.
Check.
So,
Right, so I got it closer here, so I'm at 15,000. So you can kind of start to just hone in on what the right value should
okay, so
be.
then you would go down, okay.
Yep. Yeah, it's a little bit of trial and error. Again, I hope to make this easier at some point.
Because it was at 0.6, and so,
Yeah, your question reminds me of something else too, that, this tool really is for commercial buildings, something that has 5 or more thermal zones. Right now, it does not do a good job of like single family housing, a tiny retail store with like a residential style furnace. I would not recommend Sketchbox for that. You should have at least, a large enough building to have more than one thermostat.
so more than what, 5,000 or 10,000 square feet? I mean,
I mean,
I don't know.
like let's say maybe a convenience store, like a Walgreens or something like that. A store like that, like 10, 20,000 square foot, that's going to have, 4, 5, 6 thermostats in there. So that would be an appropriate size to be modeling in here. But if you've got a, 3-foot, dentist's office or something, maybe not, right?
Shut out back.
Yeah, right. Okay, so let's see, we tweaked some things here. I'm just gonna kind of reset to this because I want to talk about measure. This is the fun part, right? So like I talked about before, my experience of modeling architectural features, and we can use that. So let's say, I'm sitting in a meeting with my architect and they want to investigate overhangs on the south facade for, let's say, just the hotel, right? So I can select from, just about every parameter that's in the tool. I can choose any of those parameters. Oops, let's do that again. So I can choose any of these parameters from the tool, like overhangs on the south. I can add it. And so the default or the baseline is 0, and maybe it's a 2-foot overhang. So I can ask a simple question and get an answer pretty quickly. That's based, in building physics. So how much does that save? Well, let's say it's 1% energy cost, 2% of electricity. I can kind of see what the impact of that is. It saves a bit of energy. It saves, $2,000 per year, right? So I asked a simple question, I got a quick answer. So you can use a tool like that. Oh, go ahead.
like when we are doing like value engineering,
Yeah.
not about the utility cost, maybe the client asks us, hey, how much confident are you with your numbers?
Yeah.
Do you think like if we do a reasonable amount of effort, put in there to model it correctly, how much do you think the confidence level would be? Hey, we are like 10-20% within.
Oh, within reason. One thing to add here is this is a simple model. Like this doesn't have the idea of an adjacent building
Right.
that might be providing some shading onto that building. That concept doesn't exist, right? So like there's limitations in what we do, but I think the strength of this really is in getting a pretty good answer that's grounded in the context of the whole building. So that's what I'm about to demonstrate here. I'm going to delete this overhang measure and just load up our, what we call our standard measure set, which is going to include like all the usual suspects. So if I collapse this, we've got roof insulation, wall insulation, air sealing, glazing, interior lighting, the high-end trim that we talked about, occupancy controls, like miscellaneous equipment power, heating efficiency, cooling efficiency, controls, like all the things are in here. And it's not all inclusive, but these are the things we typically see on a project. You can reorder these. So, if you want to apply these in a certain order, for example, if you've got a building owner that wants to get to a certain threshold and you're going to do the low hanging fruit first, you can look at it that way.
I would also ask the team here, like, would it make, if you're gonna electrify your HVAC equipment, you're also gonna improve your air sealing and insulation, which one does it make sense to do first? Maybe Ben, you can demonstrate to us here too.
Sure.
I'm just curious if anybody has an idea of what makes more sense.
The air sealing first,
And why is that?
so you can calculate the load size better
Right,
at the end.
yeah, I mean, if I make my building tighter and more insulated, my heating systems don't have to be as big. So why change the heating systems now when they still?
Right. Yeah, so I talked about good defaults too, and one of the strengths of this tool also is that we not only provide you with good baseline values, but we provide you with good engineering judgment on what your proposed or improved values should be. So like for lighting, power density is a great example because it's different for each kind of building type. So starting from a code value here, a retail store lighting power density is very different than a parking garage, right? And so is like the best practice design for each of those building types. So we're giving you some pretty good proposed values to work with too. So you don't have to like go back and, look at your past 3 jobs and try to figure out what was done, right?
Are you able to define R values for interior and exterior walls separately?
No. So the interior walls are assumed to be adiabatic, so no heat transfer on the interior.
It's the same temperature on both sides.
Yes.
Right. Okay, so for this also, we give you good, better, best values, but you can also put in your own values. So, maybe that hotel, we're going to specifically target a lighting power density 0.36, because that's what our lighting designer said they could achieve, for example. So you've got a lot of flexibility over this in these measures. You can also add measures to this list. So maybe, one thing that's not on here is improving our energy recovery ventilator. So I can find that down in the mechanical section. So energy recovery ventilation, you can add the measure. I'm going to put that down with the rest of the mechanical equipment. When I work on new buildings, I usually think about them from the outside in, right? So again, first improve the envelope, then reduce the loads, then serve them with efficient mechanical systems, and then optimize the controls for those systems. So outside in generally, but you can order it however you want, whatever makes sense for your problem. So I'm just going to change this from 50% effective ERV to 75% effective, right? So we'll add that measure to this list. So I dropped that in there. Let's see what happens there. So one thing is cool is we're not just running a baseline model and a proposed model. That's kind of the construct of compliance modeling and LEED and all kinds of other things, but that doesn't really help us make good design choices. So we're running each measure individually to see what the impact is. So you can get some high level things, right from the start. So by doing all those best case scenario measures, we can save over 40% energy, which is cool. And we can normalize things by square feet. So we do a lot of post-processing and math for you here, which is nice. This shows the energy by end use, decreasing as we apply each of our energy efficiency measures. By the time you get to this last one, these results will include the effect of all the measures before it, right? So that's important, is that we apply these progressively in the order shown so that, these results reflect the building with all of the measures included. Here again, looking at your monthly utility bills, this would show how, how that differs between baseline and proposed. Again, you can use that for calibration. It's also just a nice quality control check of your model to see that, this makes sense. We've got heating happening in winters, cooling happening in summer, right?
Can you explain that again, like how it adds up the measures?
Yeah. So back to the measure, in this case, we ran 40 something energy models. So we have got, in this design, we've got 3 different shell components, each having, 17 different changes made to those, and it's progressive. So the baseline model is just what we defined here. Then the first model that we run is the baseline, but with an upgraded roof. The second model run includes the upgraded roof and upgraded wall, right? So by the time you get down here, it's everything included.
And it's important, again, just because like if you're gonna do it over time, some things make sense to do first.
Yeah,
Like,
right.
You're gonna both put in low flow fixtures and put a new hot water heater. You'll get more savings from the hot water from changing the fixtures up front.
Right.
So you talked about energy usage intensity. Do you have a comparison of that? Just out of each model?
Yeah, so our energy use intensity here goes from 46, I'll zoom in a little bit. So 46 in the baseline case down to 25 roughly. So that's one way to track it, but I'll show you here too. So this is the chart that is most useful for energy consulting. This shows what really matters, what drives performance in this case for this model. We can look at that in terms of energy savings, but you can also look at site EUI, and we can normalize that. Well, so this is already by square foot. So this is what the impact on EUI is, right? So some of these things are a little bit negative, right? Like improving your glazing saves energy, it reduces your cooling load, but it's actually making your EUI go up because you get less free heating from that solar in the winter. So this, you can look at this a lot of different ways.
So a lot of the ordinances that you talked about, the penalties are based on what, the UI?
It's like you benchmark, it's the way that it works, the laws require you to report your energy usage. And there's a platform called the EPA Portfolio Manager. And you put in your bills, you describe what your building is like and it categorizes. It's like, all right, you're like half office, half residential. What's the average for all the other half office, half residential? Plots you on a curve, it gives you that Energy Star score, 0 to 1. So like if you are half office and half residential and half nationwide, you're using about 50% of that energy. You get an Energy Star score of 50. And all of these
But
measures.
the penalties like Birdo, which is the one I'm not familiar with, you have to pay fines if you're not meeting.
Yeah. So like
What is it that you're trying to meet, that energy use?
It's an Energy Star score. So like that's how it is in many jurisdictions. In DC, where I'm most familiar with working.
Right.
The Energy Star score for an office this round is 71. So if you put in your utility bills and you get an Energy Star score of less than 71, you're not in compliance. And there's many different ways. You can either invest some money, there's a few different ways to come into compliance, but that's like the means. And most benchmarking programs that I'm familiar with all work on the Energy Star platform.
Yeah, and I think at its core, the Energy Star is like an EUI type metric. You get credits for higher energy intense spaces, like if you've got, I don't know, a hotel, right? Like that's going to have a higher limit than an office, which is going to have a lower limit. So that's it's based on the commercial building surveys that they do, every so often at the federal level.
So, with your upgrading equipment, the heating equipment, would you want to make that change so that it is not negative and is reflective more positive?
Well, that's an
Or would
interesting,
you-
yeah, so that's an interesting one here, right? Like, so this is improving the efficiency of our heat pumps.
Right.
So it's gonna save electricity, but it's gonna make that boiler work harder to heat that water in that heat pump loop. So in this case, this is kind of an interesting one, but it's actually has a negative impact on our CO2 savings, but it has a positive impact on our, electricity savings. So you can look at this in a lot of different ways to make things about your building.
So
Most-
the first part of the predictive modeling process is to establish goals, like what you care about.
Right.
Save energy, carbonize, like what is it that you care about? To make
But
decisions.
if, 'cause I don't know, so I'm not an engineer.
Yeah,
So if I saw that, I'd be like, well, I'm losing something because I
Right.
wouldn't know that it's being more efficient because it's negative, or it shows on the graph as a negative.
yeah,
It was,
it's a-
I mean, I was
yeah.
saying that wasn't a good idea, don't do that.
Oh, you're saying don't do that,
I mean.
if you care about carbon,
right?
you wouldn't do that,
Okay.
right?
But if you cared about, let's say, your previous, your less efficient one had a refrigerant with high global warming, and the more efficient one had less global warming potential, that might be a reason to do it completely outside of energy altogether.
Right. So I'm just, before we move on to the activity, I just want to show you one more thing, and that you can start to work with costs here too. And this is a newer feature, so we don't have a lot of, defaults in here yet, but you can go in here and specify a lot. So upgrading your roof insulation, we say that maybe that's 10 cents per square foot of roof area. That's going to generate a cost for that. If I go back to my results, now I can look at that, not just in terms of like the raw energy impact it has, but what is the impact on my financials for the building. So like that has a negative net present value. So this is probably not something I would invest in. If you want to look at that in terms of simple payback, this is an 18-year payback. So that's probably not something that anyone's going to do. But if you want to add another layer of kind of value to your decision-making process, you can go through and assign costs and really look at that in a responsible economic way. I know we're kind of running close to the end of the session here. If there are more questions about the tool, I'm happy to talk through that and answer it. If it makes sense to break up into groups and try some problems, we can do that.